Hello, this is Mr. Combs. Let's talk a little bit about functions. Now, you have your information sheet this week, and it has a lot of information on it, a lot more than the video will have. So it's important that you read through the information sheet and use the video to help you fill in some of the questions that are on the information sheet. But the information sheet is going to have a lot of explanation on it, and it might not make as much sense, or the video may not make as much sense if you haven't read the information sheet as well. So make sure you do that this week. Alright, so let's talk about functions. And one of the things that we first talk about when we talk about functions is the domain and range. And you'll know from your information sheet that the domain of a function is all of the values that can be put into the function. All of the values of the first coordinate, all of the values that are associated with x. And the range is all the outputs, those values that are associated with y. So if I have a relation that is represented by this mapping, the domain basically is in the first circle and the range is in the second. So in this relation, we're not sure if it's a function yet actually, but in this relation 7 corresponds to 11, 40 corresponds to 9, 4 corresponds to 11, 9 corresponds to 25, and 3 corresponds to 10. Okay, but if I wanted to represent the domain of this, which is what this question is asking, the domain of this function, and remember we always represent the domain inside curly braces, is 7, 40, 4, 9, and 3. So that's the domain. It's just basically all of those numbers that are in the first circle. So that means that the range then is all the numbers that are in the second circle. So the range is 11, 9, 25, and 10. Alright, in the second relation, it's represented as a set of ordered pairs. So the domain is all of the first coordinates. So in this case, the domain will be -3, 3, 0, and 20. And if I want to write that in curly braces, so the domain is -3, 3, 0, and 20. And that's the domain. Now, what about the range? Well, the range is -5, 5, -5, and 5. So basically the range is made up of two elements, just -5 and 5. You don't have to write -5 or 5 twice in the range. You just have to list it once, even though it's used more than once in the relation. So -5, 5 is the range. Alright, let's look at another one. Okay, here I have a relation represented as a table of values. Okay, so I have the name of someone and then I have the number of slices of pizza that they've eaten. So in this case, the domain will be the names. So the domain in this case is Shaggy, Scooby, Velma, Fred, and Daphne. Okay? Now the range is going to be the set of numbers that represent the number of slices of pizza each person ate. So the range, in this case, is 15, 20, 4, 6, and 2. Alright? So let's look at this next one. In this case, the domain, these are probably getting boring, actually. I didn't make that one, that curly brace too nicely, so let me try again. These are probably getting boring because they're so easy. So the domain will be 6, 1, 3, and 1, but I don't have to write 1 twice. So 6, 1, and 3 is the domain. And the range is 2, 8, 2, but I don't have to write 2 twice, 5. So the range is 2, 8, and 5. Alright, excellent. Let's look at another one. Okay, here we have two mappings, and we're asked to give the domain and range of each and then determine if the relation is a function. So if you read your chart, there's a nice chart that's provided in the information sheet. It says that when you have a mapping, the way that you tell if it's a function is that each element in the domain cannot have more than one arrow extending from it. So let's first list the domain and range of these relations. Then we'll use the information in the chart to determine whether it's a function. If you hear papers rattling, that's just me pulling out my chart so I can refer to it as well. Alright, so let's take a look at the first mapping. So the first mapping, I have the elements of the domain, and they are -6, 1, 2, and 3. And the elements of the range are -8, -5, and 7. Now let's take a look at this. Remember that if this relation is a function, each element in the first circle will only have one arrow extending from it. So as I look at -6, 1, 2, and 3, that is true. -6 only has one arrow, 1 only has one arrow, 2 only has one arrow, and 3 only has one arrow. So that means that there is no element in the domain that can be mapped to two different elements in the range. So we have a function. So yes, this is a function. So I'm going to just write yes is a function. Let's try this next one. What are the elements of the domain in this case? So the domain. I'll just represent domain with a D from now on. So the elements of the domain are -8, -5, and 7. And here the elements of the range are -6, 1, 2, and 3. Now, in this case, do I have an element in the domain that has two arrows extending from it? I do. This -8 here, -8 is mapped to -6 and mapped to 1. That can't happen in a function. So this is not a function. So I'm going to say no, not a function. Okay? Here we have a table, and we're asked to do the same thing. First of all, determine the domain and range, and then to determine whether or not we have a function, whether this relation is a function. Now, in a table, there is no repeated element in the first row or column if you have a function. So let's first of all determine the domain. So the domain in this case is 0, 1. 1 is listed there twice, but I don't have to write it twice in the listing of the domain. So 0, 1, 3, and 5. And the range is 50, 60, 70, 80, 90. Alright, is this a function? You're probably saying no, because if I notice up here, I have two ones in the domain. So 1 is mapped, or 1 corresponds to 60, and 1 corresponds to 70. That can't happen in a function. So no, this is not a function. Alright. So for this table, the domain would be 30, 40, 50, 60, 70. Those are all the elements in the first column. It's the speed in miles per hour. And so if that is your speed, then the distance that you've traveled in 2 hours, that's going to be the range. And that's going to be 60, 80, 100, 120, and 140. Now, in this case, if this is a function, I can have no repeated elements in the first row, 30, 40, 50, 60, 70. I don't, so this is a function. So I'm going to say yes is a function. Okay, here we're given a set of ordered pairs. Again, we're asked to find the domain and range, and then we're asked to determine whether the relation represents a function. Okay, so for this first one, the domain in this case will be 60, 40, 20, and 60 is listed again, but I only have to list it once. So 60, 40, 20. The range in this case is going to be 30, 20, 10, and 120. 30, 20, 10, 120. Now, do I have any repeated values in the first coordinates, in the set of first coordinates in the domain? And I do, actually. I have 60 and 60, which is repeated. In a list of ordered pairs, if you have a function, there can be no repeated x value. 60 is repeated, so this is not a function. So I'm going to say no, not a function. Because 60 and 60 is the same. So let's look at this next relation. We're not sure if it's a function yet. So the domain in this case is 6, 7, and 8. 6, 7, and 8. And the range is 7, 8, and 7, but I only have to list 7 once. Excuse me. So that's going to be 7, 8 is the range. Now, when I look at 6, 7, 8, those are not, there are no repeated values in the first coordinates. The x values, there's no repeated x value, so this is a function. So yes is a function. Now, here you're asked to consider the following function using function notation. G of x is equal to x squared minus 2x, and you're asked to evaluate that function for 3, -2, and 0. So make sure you read all about in the information sheet function notation, because this might not make any sense to you unless you read that. So if you read that and you still have questions, be sure to email me or call. But let's take a look at this. When we evaluate a function, we place the given value in for the variable in that function, and we simplify. So in this case, I have g of 3. So that means that I'm going to say 3 squared minus 2 times 3. Well, 3 squared is 9, right? And 2 times 3 is 6. So here I have 9 minus 6, or 3. So g of 3 is 3. So you can think of 3 as the x value, and you can think of 3 as the y value if this were an ordered pair. So the ordered pair that would correspond to this evaluation would be 3, 3. So let's look at negative 2. So what I'm going to do is I'm going to put negative 2 in for x. So I have negative 2 squared minus 2 times negative 2. So negative 2 squared is 4. And negative 2 times negative 2 is a positive 4. So this is 4 plus 4, and that's 8. So if I were writing an ordered pair that represented this evaluation, it would be negative 2, 8. Now let's look at g of 0. So what I'm going to do is I'm going to have 0 squared minus 2 times 0. So 0 squared is 0, and 2 times 0 is 0, and 0 minus 0 is 0. So in this case, the ordered pair would be 0, 0. So that's just a little bit about evaluating functions. Okay, now we're back to determining whether each relation is a function or not. So here, something happened to my y and it got cut off. So I'm just going to list my y there. Okay, so determine if each relation is a function. Well, remember that if you have an equation, you're going to look for something done to y. If something is done to y, then probably you don't have a function. All right, so the way that you will not have a function is if you have an x value that leads to two different y values, okay? So let's look at each of these x values, use them to evaluate the function, and then we'll see if there's a chance that we can get two different y values for any one of our x values. So if I have negative 2 as an x value, and I put that into the function, I'm going to have negative 2 squared, that's 4, and 4 minus 8 is negative 4. So I'm going to get negative 4 here for y. There's no other number I can get when I evaluate negative 2 in this function. All right, let's try negative 1. Negative 1 in the function, negative 1 squared is 1, and 1 minus 8 is negative 7. There's no other way, or there's no other number that I can get when I evaluate for negative 1 other than 7. 0. 0 squared is 0, and 0 minus 8 is negative 8. And what about 1? 1 squared is 1, and 1 minus 8 is negative 7. And what about 2? 2 squared is 4, and 4 minus 8 is negative 4. So there wasn't a number for x where it allowed us to get two different y values. So I would say this is probably a function. And if we think about the chart says look for something done to y. Y is by itself, right? Y is by itself, nothing's been done to it. So yeah, this I'm going to say is a function. So I'm going to write here, yes, is a function. All right, let's look at f of x equals the square root of x. And remember that f of x is just another way to say y. So I could say y equals square root of x. Okay? So if I have -1 and I put it into the function, well, let's think about this. What is the square root of a -1? That's not real. We said that in the last unit. So that's not real. So that's not even a value in my function. That's not going to be a part of the domain. -1 cannot be a part of the domain. We'll talk more about that in a moment. What is the square root of 0? Well, it's 0. No other way I can get another number besides 0 when I put in 0. 1, the square root of that is 1. There's no other way I can get another number besides 1 when I put 1 into this function. The square root of 4 is 2. And since this radical symbol means the principal square root, the 2 is the only number I can get there. So that looks good. And the square root of 9 is 3. Again, I'm not seeing an x value that leads to more than one y value. So I'm going to say, yes, this is a function. But let's look at this last one. All right, -1. If x is -1, what can I square to get -1? Well, there's nothing, right? Anytime you square something, it's positive. So that is not part of the domain, right? So in fact, I don't know there. All right? 0. What can I square to get 0? Well, basically 0. Right? Okay, everything looks good there. Well, what can I square to get 1? Here's where the problem is. Because guess what? I can square 1 and get 1, but what else can I square and get 1? -1, right? So there are two values for this y. Notice that 1x is going to two different y's. 1 can give us 1, but it can also give us -1. Just like 4 can give us -2 as well as 2, and 9 can give us 3 as well as -3, and so on. So this is not a function. This is not a function because there are several elements in the domain x that relate or correspond to two different elements in the range y. So this is not a function, and notice what is going on here. Something is being done to y. Y is squared. So we said whenever there's something being done to y, then you probably do not have a function. All right. Now let's determine the domain of each of the following functions. So I know that each one of these things is a function. Okay, so when you have a function that's represented as an equation and you want to determine the domain, you're going to look for two things. Unless you have 0 in the denominator or a negative under the radical, the domain is all numbers, all real numbers, okay? So if we look at this first one, f of x equals x cubed plus 2x squared minus 4x plus 5, I don't see any denominators. I don't see any radicals. So I'm going to say that basically this domain is all real numbers. And I can represent that in interval notation by saying I can go from -infinity all the way to +infinity. All right, let's look for this next one. This next one, I have a radical. It's a square root. So I want to make sure I don't have a negative under the radical. So what I do is I take the radical, the radicand, 3t minus 2, and I set that greater than or equal to 0, and I solve. And the expression that I get when I solve tells me my domain. So I'm going to solve here. So I'm going to add 2 to both sides. So I have 3t is greater than or equal to 0 plus 2 is 2. And if I divide by 3, I get t is greater than or equal to 2/3. So that means that as long as the value that I put into this function is greater than or equal to 2/3, then I'm good. Okay? So I can say all numbers as long as those numbers are bigger than or equal to 2/3. But I can represent this in interval notation as well. I can start out at 2/3, and 2/3 is included, so it gets a bracket. And then I can go all the way to infinity, and infinity always gets parentheses. So this is interval notation. I could also say all real numbers greater than or equal to 2/3. Either of these things are okay. Now let's look at this next one. So this one has a denominator. It's a little bit different because it has a denominator. I need to keep 0 out of the denominator. So my technique is going to be to set the denominator equal to 0, solve, and whatever answer I get, I'm going to have to exclude that from the domain. I'm going to say the domain is all real numbers not equal to whatever I get here. So I'm going to add 3 to both sides. So I have 5x is equal to 3. And if I divide by 5, I'm going to get x is equal to 3/5. So that is what will make the denominator 0. So I can say that my domain is all real numbers not equal to 3/5. Or if I want to say this in interval notation, I can include everything except 3/5. So the way I can write this is I can say I can include negative infinity all the way up to 3/5. I'm going to put a parentheses around 3/5 to show that I'm not including it, and I'm going to union that with 3/5 with a parentheses to show that I'm not including that, all the way to positive infinity. Okay? All right. Let's look at this next one. So I have a denominator again, so I'm going to set t squared equal, or plus, excuse me, t squared plus 1 equal to 0. Now, let's see if I can solve this. I'm going to say t squared is equal to negative 1 because I'm going to subtract 1 from both sides. And basically, t squared is equal to negative 1. That has no solution. That has no solution because there's no number that when you square it, the result is negative. So this is no solution. And that means that there's nothing I have to exclude. So the domain here is all real numbers. And I can represent that in interval notation by saying negative infinity all the way to positive infinity. All right, let's look at 2 more that ask us to find the domain given an equation. All right, so in this case, I have a denominator. So I need to take that denominator and set it equal to 0. So I'm going to say 2x squared plus 5x minus 3 is equal to 0. Now this right here is something I'm going to have to factor. So I need to factor this. So since we're not dealing with factoring here, I'm going to go ahead and factor this for you. So use your favorite method to factor this. When I factored this, I got 2x minus 1 and x plus 3 as my binomials. Okay, you might need to go back to the factoring review in a previous unit that we had if you have trouble factoring this here. But this is the two binomials. These are the two binomials, excuse me. And so now I'm going to set each one equal to 0. So 2x minus 1 equals 0. And x plus 3 equals 0. So if I add 1 to both sides here, then I'm going to have 2x is equal to 1. And if I divide by 2, I'm going to have x is equal to 1/2. And here, if I subtract 3 from both sides, I'm going to have x is equal to -3. So basically, I have to say that the domain in this case is all real numbers not equal to 1/2 or -3. Or in interval notation, remember I have to exclude both of these numbers. So I can say I can have negative infinity all the way up to -3 union, and I'm going to have to do some little fitting in here. Union that with -3 all the way to 1/2. I'm going to union that with 1/2 all the way to positive infinity, and I've excluded the -3 and the 1/2 by using interval notation. Alright, let's look at one more. So here I have something underneath the radical. I have 9 minus 3t. So I'm going to take 9 minus 3t, and I'm going to set that greater than or equal to 0. So what I'm going to do is I'm going to add 3t to both sides. So I'm going to get 9 is greater than or equal to 3t, and if I divide by 3, I'm going to get t is greater than or equal to is less than or equal to 3. So if I switch this around, t is less than or equal to 3. Excuse me, I didn't have my pen turned on. So t is less than or equal to 3. So basically the domain is all real numbers less than or equal to 3. And so I start out with 3, and that is included, but I want everything that is 3 or less, so I use negative infinity, and that's how I write that in interval notation. Okay, so the last way that we can have a function represented is as a graph. And here we're asked to tell whether each of these is a function or not. And we can use something called the vertical line test. Now, this is all in your information sheet. If a vertical line crosses the graph in more than one place, then you do not have a function. Okay, so let's look at each of these graphs. Okay, so let's look at this first one. Well, really, I see a vertical line already that crosses this graph in more than one place. The y-axis itself is a vertical line, and I have 1 crossing, 2 crossings, 3 crossings. So this certainly isn't a function. This is not a function. Not a function. Does not pass the vertical line test. We could even say not a function by VLT. So it doesn't pass the vertical line test. This one, however, does. No matter where I draw a vertical line, it's only going to pass this graph in one place. So this is a function by VLT. What do you think about this circle here? Or it's not a circle, it's sort of an oval shape here. Well, let's draw a vertical line. Look, I'm crossing it in more than one place. So not a function. But this one is a function because a vertical line doesn't cross it in more than one place no matter where I draw it. So this one is a function. Okay, now how do I determine the domain and range given a graph? Well, to find the domain of a function given a graph, we're going to look where the function occurs along the x-axis. To find the range, we're going to look where the function occurs along the y-axis. Okay, so let's take a look at this first one. So here I have this graph, and basically if you notice it has arrows on the top, so this graph is basically going to get wider and wider, and it's going to go up further and further. So it's going to continue to go up further and further and further and further and further in here as I go. So eventually it's going to, no matter how far along or how far over here I start, the graph is going to actually occur. I can actually take a line, or I can go from the x-axis up and hit a portion of the graph. So it's going to occur no matter where I go along the x-axis. So basically the domain of this function is going to be all real numbers, so negative infinity to infinity, because it occurs all along the x-axis. But the range is a different matter. If I travel along the x-axis, I only start to get function if I follow along the y-axis, I only start to get the function defined, or the function occurring, when y is 1, 2, negative 2. See where y is negative 2? And then from there on out, I keep getting function. So the range in this case is going to start out at negative 2, and negative 2 is included. But then I'm going to go on to infinity. Does that make sense? All right, let's look here. Here I don't have function all along the x-axis. If I'm traveling along the x-axis, I only start to get function right here. And this is, let's see, 1, 2, 3, 4. I know this is kind of small. So I only start to get function at negative 4, x equals negative 4, but then I go on forever. So the domain in this case is going to start at negative 4 and then go on to infinity. Where do I start getting range if I'm looking at the range? The range only starts here at 0, right? So I start at 0, but then I continue because this arrow means I'm going to go up and up and up and up and up. So I will get range from then on. So the range in this case starts at 0, but it goes on to positive infinity. Actually, that's a little hard to see as green on this. So I'm going to say the range starts at 0 and goes on to positive infinity. Uh-oh. This doesn't look too good. Okay, now that looks better. Alright, so let's look at this one right here. So in this case, again, I'm going to get the function covers the entire x-axis because it goes on forever. So the domain is going to be, again, negative infinity to infinity. But I only start getting the function along the y-axis at y is equal to 2. So the range, is going to be 2, and 2 is included, all the way up to positive infinity. Alright, in this case, this is a line, and something interesting about a line is the domain and range for a line will always be all real numbers, or negative infinity to positive infinity. So the domain here, because look, no matter where I go along the x-axis, I can always draw a line up to the function, then that's going to be always infinity, negative infinity to infinity. And because no matter where I am on the y-axis, since this function goes on forever, I'm always going to have function along the y-axis. That's the range is also, and let's see, the range is also negative infinity to infinity. All right, let's look at these last two here. So here, the domain is not going to be the entire x-axis. I only start getting function at x is 1, 2, 2, right? So the domain in this case is going to start at 2. So 2, and it gets a bracket. But it's going to go on forever. So it's going to go all the way over to infinity. All right. The range, on the other hand, though, will start at 0. Right? So the range starts here at 0. This is where y equals 0. And then as it goes on forever, it's not, I mean, I know this looks like it levels off, but this arrow means that it's not going to level off. It's going to keep going up and up and up. I'm going to have that to infinity. So the range is going to be 0 to positive infinity. Now let's look at this one. This one's a little bit different. Again, since I have arrows, it's going to extend forever along the x-axis. So the domain in this case, again, is going to be all real numbers. So negative infinity to positive infinity. But here, the range, well, I'm getting range. I mean, as the function goes down, I'm getting range, right? So it looks like that I'm going to have range all the way to negative infinity. There's no end to the range, but the range stops when I get to 1, 2, 3, 4, right? When I get here, the range stops. There's no function above 4. So this is going to be from negative infinity all the way to 4, but 4 is included. And I hope that this helps. If not, just give me, shoot me an email or give me a call, because I realize that functions are something that's not that common. I mean, you've probably not studied functions before, or if you have, you know, probably not. You've not gone in depth. So I realize this is sort of a new concept. So just let me know if you have any trouble. And I will see you next time.